Here comes the sky.
Elliptical orbits with angular momentum. Conservation of angular momentum is one of the two laws that govern elliptical orbits. This animation shows gravitational force F, which is red, and the velocity v, which is green, of the object as it orbits the ellipse. Note that the velocity is tangent to the path, which it always is. The force always points towards the central body, just like a normal circle. A force pointing towards the center produces no torque, which is why angular momentum is conserved. The angular momentum of the object about the central body can be calculated in one of two ways. L equals I times omega, where I equals mr squared, increases as the planet gets farther away, and omega, which is your angle over time, increases as the planet makes a bigger angle around the star. In the graph, notice how the omega, which is on the x-axis, increases as I decreases, but the area of the rectangle of the I and omega square diagram will stay the same. That's because, again, there is no external torque, so angular momentum is conserved. The other way to calculate angular momentum is L equals mvr sine theta, where m is the planet's mass, v is the speed at some instant, r is its distance from the star, and theta is the angle between v and r. Here we have r sine theta on the x-axis and mv, our linear momentum, on the y-axis. The vector r from the star to the planet is in blue, and the vector v in green is tangent to the orbital path. The square chart shows how mv decreases as r sine theta increases, but the product, the area, stays the same. Suppose that A is one point in the object's orbit where it has speed v sub a and distance to star r sub a, and the angle between the speed and radius is theta a. Suppose B is another point with vb, rb, and theta b. We can write a conservation of angular momentum equation. All of our momentum in the beginning equals all of our momentum in the end. That's conservation of angular momentum. Conservation of linear momentum also. So we're using mvr sine theta for each side. This is one of the two equations that describes an elliptical orbit.